Oh, yeah. It's not that we don't understand thermodynamics. We don't understand how thermodynamics applies to gravity. Um, in thermodynamics, um, we can either write, write down the laws of thermodynamics, but then we have to talk about energy. The first principle of thermodynamic energy is conserved. And in gravity, energy is a funny thing. There's not a global, well-defined energy. Energy is depending of there are a number of different notions of energies which don't match in general. Um, if you think in terms of statistical mechanics, which is sort of the underpinning understanding of thermodynamics, we understand thermodynamics as the behavior of many degrees of freedom statistically, right? Heat is the motion of the molecules very fast. Once again, statistical mechanics, I mean, takes the most common formulation. You say that everything can be described assuming, like Boltzmann, that the state is e to the minus beta h, where h is Hamiltonian. Now, in general relativity, the Hamiltonian is zero, strictly zero, because of the peculiar, precisely because of this um, um, dilation of time and compression of time. Standard thermodynamics assumes a common time that passes equal for everybody.
Hmm.
This is not there in general relativity. So we have to re-understand thermodynamics in a general relativistic setting, or equivalently, we have to understand how the gravitational field behave thermodynamically. And the point is that we don't have this theory. We don't have a thermodynamics of gravity. Now, when we apply thermodynamical idea to black holes, we don't need the full thermodynamics of gravity. We just make some guesses, some assumptions, and we go. Some of these guesses may well be wrong.
I see. I see. So we're pushing theories a little bit beyond where they should be pushed, and then we're
Yeah,
coming. I see. And then
yeah.
we're running into
But
trouble.
but I think that there is a specific mistake that people do,
Hmm.
uh, in which is the origin, the actual origin of most of the confusion in the current discussion, which has to do with entropy.
Hmm.
People often talk about the entropy of a black hole, the entropy of something, and this is okay. But the problem is that we have different notions of entropy, and they are not always the same. And in particular, for black holes, there are two different notions of entropy that get confused, and this gives rise to the problem. A black hole, a big black hole, is hot
Hmm.
and emits radiation, just like a hot stove. You can throw energy into it. You can take away energy. You can do things with it. So it is a thermodynamical object. So it has an entropy, and in some beautiful guesses that goes back to John Wheeler and Bekenstein, and then Hawking, uh, they realize that the entropy of the black hole is exactly proportional to the surface area, okay, to the area of the black hole. So a big black hole has a lot of entropy, a small black hole has little entropy. And this is thermodynamical entropy. It's the entropy that describes the thermodynamical behavior. That's very beautiful because entropy is information,
Hmm.
roughly. It's connected. So when you have some entropy outside and you throw it in the black hole, the area grows. So it's like the entropy keep growing, that's the second law of thermodynamics. And if you throw some information inside, you lose entropy, but the area increases. So you say, oh, great. The total entropy keep increasing because the outside entropy and the area both increase together. That's a so-called generalized second law. So it's the second law plus the entropy of a black hole. That's all fine. That's kosher, beautiful, fantastic. Okay. But then, and that's a mistake, people say, oh, there's another entropy. That's called the von Neumann entropy. Okay, what is a von Neumann entropy? Remember, we said if you have two systems, they can be entangled. The state is pure, but if you just look at one system, the state is not pure
Hmm.
because it's entangled with the other, and so you can compute its entropy. And there's a formula written by von Neumann that gives its entropy. Now, very often, the von Neumann entropy and the thermodynamical entropy are the same or strictly connected to one another. Very, very often. So people say, oh, if it is true very often, it has to be true for black holes. And they're wrong. Yeah, they're completely wrong. They're wrong because when the black hole shrinks, okay, it becomes smaller, 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 the area becomes smaller. So the thermodynamical entropy becomes smaller. As a thermodynamical object, it behaves like, a smaller cup of hot water, has less entropy. Okay. But remember, this is gravity. Inside, the volume is not small. Volume is colossal. Inside, there's room for everything. So you can be entangled with very, very far away things inside, deep inside, with degrees of freedom that don't contribute to the thermodynamic entropy. They don't play any role thermodynamically because they're deep inside. Just by locality, they're too far for affecting anything of the heat and work exchanges. So the von Neumann entropy, the amount of things you can be correlated can be colossal, even if the thermodynamic entity is small. And that's where people go wrong. Because people, they say, look, the thermodynamic entity is small, therefore, for sure, the von Neumann entropy must be small. Therefore, the outside state cannot be correlated with the end state, and therefore, information should come out before in some crazy way. And they miss the point that the von Neumann entropy can be larger than the thermodynamic entropy, which is something every condensed matter physicist know. But fundamental physicists who think about cosmology, black holes, don't read condensed matter physics papers. So they are under the wrong, they confuse different kind of entropies. And sometimes I talk with colleagues, very good colleagues, and they say, the entropy of a black hole. I mean, what do you mean exactly by entropy? The entropy. Something has an entropy. It's the entropy. Okay? And they say, wait, I mean, it's not the entropy. There's entropy one side, and the other side is... And that's the source of the confusion.
So the take-home message here, let me see if I follow you. So you're saying that as the black hole evaporates, it releases Hawking radiation. That radiation is thermal, right? And it doesn't carry away information.
Exactly.
The information is
It's
contained.
inside.
It's inside the black hole, and the black hole can contain more information than you would otherwise think because there's this difference between the two types of entropy.
Precisely.